We tend to think of the Earth as just a big solid rock that we live on, but that's not the whole story. It's not static, it's a dynamic, powerful machine. Our goal for this standard, HS-ESS2-1, is to understand Earth as a complete system. We're going to connect the dots between giant, deep events like volcanic eruptions, which are driven by heat from inside the planet, and surface events like weather and erosion, which are driven by energy from the outside, the sun. By the end, you'll see how a process in the middle of the ocean can affect the air you breathe. So what do we mean by a system? A system is just any group of parts that interact with each other. Think about a car engine. It has pistons, fuel, and electrical parts. You can't just look at the spark plug alone and understand how the car moves. You have to see how it interacts with the fuel and the pistons. The Earth is the same, but its parts are rock, water, air, and life. These parts are constantly exchanging both matter, like water moving from the ocean to the air, and energy, like sunlight heating the land. The most important concept is feedback. If you push on one part of the system, like the atmosphere, it will cause a change in another part, like the ice caps. To make sense of this giant system, scientists break it down into 4 main parts, or spheres. The first is the geosphere. This is all the rock, the solid stuff. That includes the mountains you see, the ground under your feet, and all the molten rock deep in the mantle. Next is the hydrosphere. This is easy. It's all of Earth's water, oceans, rivers, and lakes, but also the massive ice sheets in Antarctica and even the water trapped in the ground, called groundwater. The atmosphere is the blanket of air that surrounds the planet, giving us weather and protecting us from space. And finally, the biosphere, which is all life, from the smallest bacteria to the biggest whale, including us. The key is, none of these spheres is separate. They are all tangled together. The official standard we're covering, HS-ESS2-1, asks us to develop a model. That's a sciencey way of saying, explain the connections. This isn't just about memorizing the definition of a volcano. It's about being able to explain how that volcano, part of the geosphere, can change the atmosphere or the hydrosphere. We need to build a mental map of how Earth works. How does a surface process, like a rainstorm, connect to an internal process, like mountain building? It's all about finding the links, the causes, and the effects that tie the entire planet together. To understand why anything happens, you have to follow the energy. Think of the Earth as a machine that runs on 2 different engines at the same time. The first engine is internal. It's the incredible heat trapped in the Earth's core and mantle. This engine powers all the deep geologic processes. The second engine is external. It's the sun. The sun's energy, or solar radiation, hits the surface of the planet and powers everything we see on top. Our weather, the water cycle, ocean currents, and even life itself. These 2 engines, one working from the inside out, the other from the outside in, are what make our planet so dynamic. Let's look at that first engine, the internal heat. Where does it even come from? A lot of it is residual heat, literally leftovers from when the planet first formed, 4.5 billion years ago, from crashing asteroids and gravity. The other major source is the slow, constant radioactive decay of elements like uranium and potassium in the mantle. It's like a giant, slow-burning nuclear battery deep underground. All that heat creates immense pressure and energy that has to go somewhere. It can't stay trapped, so it slowly works its way to the surface, driving the processes of the geosphere. So how does this heat move? It moves through a process called mantle convection. It's the exact same principle as a pot of boiling water or a lava lamp. When you heat the bottom of the pot, the water at the bottom gets hot expands, and becomes less dense, so it rises. When it hits the cool air at the top, it cools down, becomes denser, and sinks, only to be heated again. The same thing happens in Earth's mantle. This rock is so hot it actually flows very, very slowly, like thick tar. Hot rock rises, cool rock sinks, creating huge circular currents called convection cells. These cells are the mechanism that moves the solid crust above them. And the result of that mantle convection is plate tectonics. The Earth's crust, which we call the lithosphere, isn't one solid shell. It's broken into a puzzle of giant pieces like a cracked eggshell. These pieces are the plates. Because they are floating on top of that gooey, convecting mantle, the mantle's movement literally drags them around. This is the grand unifying theory of geology. It explains why we have continents, why we have oceans, and why they aren't in the same place they were 100 million years ago. The action of plate tectonics happens at the boundaries, the edges where two plates meet. There are three main types. First are convergent boundaries, where two plates crash into each other. This collision is what builds massive mountain ranges like the Himalayas. Second are divergent boundaries, where two plates pull apart from each other. This allows magma from the mantle to rise up and create new crust, like the Mid-Atlantic Ridge. And third are transform boundaries, where two plates just slide past each other sideways. This is what causes massive earthquakes, like those on the San Andreas Fault in California. So, to summarize that first engine, it all starts with internal heat from the core. This heat creates mantle convection. That convection moves the tectonic plates, and the movement of those plates at their boundaries is what directly causes the biggest geologic events we know: earthquakes, volcanic eruptions, and the slow, powerful construction of entire mountain ranges. All of these are geosphere events driven from inside the planet. Now for the second engine, the sun. This one is all about the surface. The sun's energy, called solar insolation, hits the Earth. But it doesn't heat the planet evenly. The equator gets very direct, intense sunlight, while the poles get weak, angled sunlight. This uneven heating is the single most important driver for our climate and weather. Air at the equator gets hot and rises, while cold air at the poles sinks. This creates global wind patterns. This same uneven heating, combined with wind, drives the massive currents in our oceans. The most obvious job of the solar engine is powering the water cycle. It's pretty simple. The sun's heat provides the energy for evaporation, turning liquid water from oceans and lakes into water vapor, gas in the atmosphere. That vapor rises, cools, and condenses into clouds. Then, gravity, another key force in surface processes, pulls that water back down as precipitation, rain, or snow. This cycle is a perfect link. The atmosphere holds the moisture. The hydrosphere is the water itself, and it falls onto the geosphere, or the land. When that rain, hydrosphere, hits the mountains, geosphere, it starts to cause weathering. Weathering is just the process of breaking down rock into smaller pieces. This can be physical, like ice freezing and cracking a rock, or chemical, like acid rain dissolving limestone. Once the rock is broken, it gets moved. This movement is called erosion. A river, powered by gravity, can carve a canyon. A glacier can gouge a valley, or wind can create sand dunes. Finally, deposition is when that sediment is dropped in a new place, like a river delta at the mouth of the ocean. These processes are constantly reshaping our planet's surface. The rock cycle is the perfect model for linking both engines, the internal heat engine and the external solar engine. It shows how they work together as one big system. Let's start at the surface. The solar engine powers weathering and erosion, which breaks down a mountain and carries the sediment, sand, silt, to the ocean. That sediment builds up in layers. As it gets buried deeper and deeper, the internal heat engine takes over. The intense pressure and heat cook the sediment, turning it into metamorphic rock. If it gets hot enough, it melts completely into magma, which might then erupt from a volcano, cool, and form new igneous rock. That new rock is then pushed up to the surface, where the sun's energy starts weathering it all over again. Let's trace a real-world example of this system interaction. In 1991, Mount Pinatubo in the Philippines erupted. This is a geosphere event, driven by internal heat and plate tectonics. It was a massive eruption. It shot millions of tons of ash and sulfur dioxide gas high into the atmosphere. This cloud of gas and ash spread around the entire globe and literally reflected sunlight back into space. The result? The entire planet's average temperature dropped by about 1 degree Fahrenheit for 2 years. This affected the hydrosphere, ocean temps, and the biosphere, crop failures. One geosphere event changed the entire global climate. Here's a simpler interaction that happens every day: photosynthesis. This is a biosphere process. A plant, life, needs resources to grow. So it interacts with the other spheres. It pulls CO2 from the atmosphere. It pulls water from the hydrosphere, using its roots in the ground. And it pulls nutrients from the geosphere, the soil. It's a perfect little model of all 4 spheres interacting. And if that plant dies and gets buried for millions of years, its carbon can get compressed and become coal, which is now part of the geosphere. If you want to see the ultimate example of a system, look at the carbon cycle. Carbon is the building block of life, and it moves through all 4 spheres. It's in the atmosphere as carbon dioxide, CO2. The ocean, or hydrosphere, absorbs massive amounts of that CO2. The biosphere, plants and algae, pulls it from the air and water through photosynthesis to build their bodies. When they die, their carbon can be buried, forming rocks like limestone or fossil fuels, locking it away in the geosphere. When we burn those fossil fuels, we are taking carbon from the geosphere and putting it back into the atmosphere, creating a massive change in the system that we call climate change. It's important to remember that these processes don't all happen at the same speed or size. We have to think on different scales. The temporal scale, or time, can be incredibly fast or incredibly slow. An earthquake can shift a landscape in seconds. But the tectonic collision that built the mountains for that earthquake to happen in took tens of millions of years. The same goes for the spatial scale, or size. Chemical weathering can happen to a single microscopic mineral grain. At the exact same time, a continent-sized tectonic plate is moving, and a planet-sized climate system is operating. So back to our main goal. How do we model a system this big and complex? A model is just any representation of a system that helps us understand it. A diagram of the carbon cycle on a whiteboard is a model. It's a flowchart that shows the inputs, outputs, and connections. If you build a stream table with sand and water in a lab to see how a river forms a delta, that is a physical model. And today, the most powerful models are complex computer simulations. Scientists input data about the sun, the oceans, and CO2 levels to create a simulation that models global climate change, helping us predict how the system will react. So what's the big takeaway from all this? The most important thing to remember is that Earth is a single, integrated system. You can't just study the oceans, or just the atmosphere, or just the rocks in isolation. They are all connected. The planet is powered by 2 main engines: the internal heat from its core, which drives the deep geosphere processes like tectonics, and the external energy from the sun, which drives the surface processes like weather and erosion. A change in any one part of this system, whether it's a volcano erupting or humans adding CO2 to the air will cause feedback effects in all the other parts.